so excited to be here with you all today. I wish I could see your faces, but I understand the bandwidth challenges, probably more than a lot of other humans in this world do. So we will focus in on actually, and Rach, we need to switch the display settings on this one because you're showing the, yeah, there we go. Okay, so today we're going to talk a little bit about how what is in the ocean, the sand in the ocean, goes to becoming cloud computing, the experience that you're having, playing Minecraft with a bunch of other people via the internet, how that works to some extent. We won't get into all the details of TCP or anything else like that, but we'll kind of get into how that function, that flow, that supply chain even is managed to be able to deliver end user experiences that are transforming our world. And I hope, my greatest hope is that you come away from this that much more excited to create and learn this kind of technology. There's just, the world is the limit. So let's jump on in. A little bit about me. So Jesse already did a little bit of an intro. I have two adorable little humans that I am blessed enough to be the mom of. They're over there on the left side of your screen. That's Cyrus and Maxwell. And I saw in the chat earlier that some of you are heading to Hawaii this summer. Congratulations, it's an amazing place. This shot is actually from the big island of Hawaii in December of last year when remote working was clearly going to be here for a while. And it wasn't really safe to be with all of our family. My husband, David, who's there holding little Cyrus. And I decided, you know what? We're in technology. We can work from anywhere. So we're just going to relocate and live in Hawaii for a month. And so I did. I got up at 4:30 every morning to go run before my work started at 6 in the morning, which is, 8 a.m. PS standard time. But it was such a great experience. And again, one of those wonderful things about being in this industry of technology, it connects us everywhere, and it's able to enable you to live your life in very different ways. That center shot is actually from a stage, I believe in Taiwan, if I'm remembering correctly, where I was doing a talk with a bunch of our customers and our partners about hyperscale computing, some of the challenges of operating true hyperscale data centers, the heterogeneity of it, the networking complexity of it, even aspects of sustainability and how that has to be managed moving forward in the industry. And so it was a really amazing opportunity. And I've been super blessed in my journey at Intel. Before that, I was at Synopsys, I was at ATI, I was at SGI. So I've spent my whole life in the domain space of semiconductors and in the area of electronic design automation software, which is the software that we use to design and validate semiconductors. So this is my passion, this is my baby. I went to college at MIT. I got my BS in computer science and electrical engineering. Even then, even through my first internships, I kind of started in computer science in that world of coding. And I found that I was really drawn to electrical engineering because it was such a known domain space. In computer science, you can do everything from, coding up games to actually working in robotics to working in all these different domain spaces. That felt very theoretical to me in college. And when I was able to get my hands on hardware, you're in the world of physics and things actually have to operate. And for some reason, for me, that, I'm a more kind of concrete hands-on human. So for me, that was really very nice. I liked knowing that there was a limitation in some sense, because it meant I had to actually make something operate and be delivered at the end, versus I think a lot of coding projects, you get started on them and then people change direction and then you have to start again and start again and start again. So anyway, everything is very different. Both fields are amazing. My husband's actually in computer science as well and more in the entrepreneurial space. So I get to see a lot of it every day. And I think, both are just amazing areas in terms of pursuit for career. And the last picture is kind of a funny face, but I also am very much into music. I don't know if you can see my guitar in the background or not, but I sing in a band. I've been singing in that band for over 15 years, if you can believe it. The band's name is Sinister Dexter, which is for Sinistra Dextra in Latin. I don't know if I saw that many countries from Latin roots, but that really is because if you think it stands for left and right, and we're a bunch of hardware and software engineering nerds who make music together. So we use our left and our right brains. So we're Sinister Dexter. Anyway, it's kind of nerdy, but I couldn't imagine a more fantastic and wonderful set of humans. And music is one of those other areas where you get to be so creative, and you get to use a lot of technology and a lot of there's a lot of fun and cool tech in that domain space as well. So super passionate about it. So about 6 years ago, I came to Intel, and I love Intel. I love Intel because we are a platform company. We are a solutions and a services company. Our whole job every day is to create world-changing technology to enrich the lives of every person on Earth. And I think all technology has that capacity, but some things are better enabling maybe at doing it than others. And certainly I think computation is one of the necessary things to make sure that our world works. So AI, robotics, gaming, everything that we were talking about earlier, they all need to run on computers. And that's what we do every day, among other things. So we are inspired to drive innovation, to harness and reach out around the globe to build a better society, business, and planet. And we do a lot in terms of our sustainability goals to try and make sure that this world is a better place through technology. And you know, I personally love this part of our culture. We're here to push ourselves and to push our industry and our peers to be better and to make sure that the world is a better place. So we have big ambitions. We love what we do, and I'm glad to be here with you. And I wanted to, just like Jesse shared a little bit about Create and Learn, I wanted to share a little bit about Intel's history, how Intel was born. What you're seeing on that shot as Rachel's pulling up the video is, you know, Jeffrey Moore, who's one of our founders, the inventor of Moore's Law, and all of the work that's happened to kind of bring transistors to scale in computing. And I wanted to share a little bit about that with you. So go for it, Rach.
Take a huge computer to do. Its story dates to a year that David Pogue reminds us isn't exactly known for its good times.
In many ways, 1968 is famous for its tragedies, assassinations, conflicts, and war. But 1968 also gave birth to something amazing, the era of fast, cheap, ubiquitous electronics. Because 50 years ago, this past week, two middle-aged engineers quit their jobs to start a new company called Intel.
In 1968, Gordon Moore dropped by Bob Noyce's house. Bob was mowing the lawn. They were discussing the state of their current jobs, as well as the possibility of a new industry.
Elizabeth Jones is Intel's archivist. She runs the Intel Museum in Santa Clara, California.
And apparently Bob said, yeah, that's a good idea.
He did, and on July 18th, 1968, Intel was incorporated.
At his previous company, Fairchild Semiconductor, Noyce had co-invented the integrated circuit, a way to etch all the circuits in that era's room-sized computers onto a tiny slice of silicon.
We have Intel's first product. It's a memory chip called the 3101.
Okay, and before that, how did they make memory?
It's this larger device up on top called core memory.
Smaller also meant faster and easier to make. This plant near Portland, Oregon, one of Intel's oldest, is what a chip factory looks like today. No TV crew has ever been allowed inside before.
Do you have this in a khaki?
No, I'm sorry.
Aisha Evans, Intel's chief strategy officer, showed me how to put on the so-called bunny suit. That's her on the left.
I did take a thorough shower this morning. Why was all this necessary?
We want maximum purity as the material is being assembled.
Each shiny round sheet of silicon fits about 500 identical chips, which will be cut apart and installed into the microprocessors the electronic brains that control just about everything in our lives with an on switch. Each chip is etched with impossibly small channels of circuitry, only 10 millionths of an inch wide.
And so, who gets to etch those tiny, is it some little Swiss watchmaker with a magnifying glass?
Robots.
So how would you say the making of silicon chips has changed in 50 years?
You know what? The basic principles and fundamentals haven't changed at all. Just a lot more automation, a lot more complexity, and also more layers.
I see, and that's to get more circuitry into less space.
That's exactly right.
Getting more circuitry into less space is the whole point of Moore's law. That's Gordon Moore's prediction, way back in 1965, that we'd be able to double the amount of circuitry, meaning power and memory, that can be crammed onto a chip about every year and a half. He's basically been right for all 50 years.
So I got a great question in chat that asks, hey, why are they wearing all that gear? They just look silly. They didn't say that, but I'll pretend that that's what they're wearing. So it's actually when we are in one of the fabrication facilities to turn sand into these silicon wafers, the purity of the silicon that's required for you to be able to actually etch that wafer and have good quality and actually operate and have, you know, the electronic signal go exactly the way that you want with any kind of leakage not happening, leakage being current or, you know, basically power doing things you don't expect it to do. To make that happen, you actually have to have fewer than 1 part per million of any kind of outside particles, particulate matter. So there's a very, very strict protocol to keep, there's a huge amount. I mean, I'm sure during COVID, many of you have heard about HEPA filters and different ways in which we try and make sure that the air quality, or maybe if you've lived through the wildfires here on the West Coast of the United States and around the world, you know, there's a lot of things that we do to try and purify the air to keep it safe for humans to breathe. There's a lot that we can breathe. Silicon does not want any of that in there. So we go through basically, you know, vacuum sealing to make sure that as little crud is in that environment as possible so that we have higher yields for our silicon in the production space. So anyway, this is, you know, a microchip. And I think you saw a little bit in that video. I wanted you to be able to see a little bit in that video of how they come together, what it looks like, what a fabrication facility looks like, how people get dressed up and turn that silicon into the microprocessors that are in your phone, in your headset, all of those other factors. And a little bit about how, you know, this company that started in 1968 with, you know, this entire transition to transistors became a processor company. I know what a microchip is, and I actually want, you have a lot of microchips in there. Okay, so maybe let's take one more, I want to do one more video to kind of help anchor in on how we actually go through the process of making a transistor, making a microchip.
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch, 10,000 times smaller than a human hair, that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once inside an Intel fab, the raw wafers begin their long journey through an incredibly complex process. They're loaded into front-opening unified pods, or FOUPs, which travel hundreds of miles along Intel's automated superhighway, going from tool to tool, as processors are painstakingly built up on each wafer. The wafer first goes through a series of important steps, such as photolithography, ion implantation, and etching, that prepare it for the critical transistor formation process. Intel was the first to manufacture three-dimensional transistors called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate in order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation, Intel's integrated design and manufacturing capabilities have enabled humanity to innovate game-changing technologies that impact nearly every facet of modern life. Intel keeps powering the world. At the same time, we're powered by you, the makers, the dreamers, the doers, the people who share in our history of making the world smarter, faster, and more connected.
So maybe I'll just, to help you understand, I live this world of manufacturing processors, manufacturing microchips. But I also work with end users to try and make that into end experiences, things like gaming. So I wanted to give you a sense of what it takes to build these systems and then how we can actually use them. So maybe we'll take one step forward or 5 steps forward and then come back, and hopefully it'll make sense by the end. So when you're thinking about your experience of playing Roblox, this is dependent on something that we call cloud computing. Lots of people in the world talk about the cloud, going to the cloud, backing up in the cloud. I'm sure you've heard some form of something out there on that. But the cloud is really just a way of describing how an end user experience through a device, whether it's your iPad or your phone or any kind of computer, is actually connected to a series of applications on the back end. That overall cloud can be constructed in many different ways, and it actually doesn't matter. The internet makes that possible. Everything has a known abstraction layer so that your end user experience can be vended to you in a very specific way. So what are the components that are necessary for the internet to deliver cloud computing? One is networking, right? You might have found at times that your parents, when you were home, on these kinds of calls, and they were also trying to work from home during COVID, that the internet, your network at home wasn't running as well as you would like. Mostly your network at home is far less bandwidth than the backhaul of the internet. And maybe you have a wireless network in your house that you've heard about, Wi-Fi in your house. That's networking. That's the back-end connection that sends data from one point, the client, your iPad, let's say, or your computer, back into the internet so that you're using the cloud. So you have to have networking. Then there's applications. Software applications, I think this is where you guys have probably spent the most of your time as you're programming. These are applications. This might be a game. This might be social media. It might be any number of things, but those are the end user applications that you use that are enabled through the internet. Security is another incredibly important part, which is worth an hour all to itself. And I won't necessarily get into the details of how backend and network security can be done. Data storage. So a lot of the internet is actually it's keeping information about what you use. So when you log into your game, it remembers your previous state, it remembers your avatar maybe, it remembers where you were in the game. That memory of what you did, that's storage, right? And then the last thing that, from my lens, working in business, working with different businesses, that a lot of cloud computing enables is business intelligence. What does that mean? It's kind of a soft word, but what we mean is being able to collect data about how users are using our products and then use that to improve end user experiences so that we can become better at serving these software applications. So these are core components of how cloud computing works. Maybe we'll do one little one on that.
Cloud computing is the on-demand delivery of IT resources via the internet, with pay-as-you-go pricing. Instead of buying, owning, and maintaining physical data centers and servers, you can access technology services such as computing power, storage, and databases on an as-needed basis from a cloud provider like Amazon Web Services. Organizations of every type, size, and industry are using the cloud for a wide variety of use cases, such as data backup, disaster recovery, email, virtual desktops, software development and testing, big data analytics, and customer-facing web applications. For example, healthcare companies are using the cloud to develop more personalized treatments for patients. Financial services companies are using the cloud to power real-time fraud detection and prevention. And video game makers are using the cloud to deliver online games to millions of players around the world. With cloud computing, your business can become more agile, reduce costs, instantly scale, and deploy globally in minutes. Cloud computing gives you instant access to a broad range of technologies so you can innovate faster and build nearly anything you can imagine. From infrastructure services such as compute, storage, and databases, to Internet of Things, machine learning, data analytics, and much more. You can deploy technology services in a matter of minutes and get from idea to implementation several orders of magnitude faster than before. This gives you the freedom to experiment and test new ideas to differentiate customer experiences and transform your business, such as adding machine learning and intelligence to your applications in order to personalize experiences for your customers and improve their engagement. You don't need to make large upfront investments in hardware and overpay for capacity you don't use. Instead, you can trade capital expense for variable expense and only pay for IT as you consume it. With cloud computing, you access resources from the cloud in real time, as they're needed. You can scale these resources up and down to grow or shrink capacity instantly as your business needs change. cloud computing also makes it easy to expand to new regions and deploy globally in minutes. For example, Amazon Web Services has infrastructure all over the world, so you're able to deploy your application in multiple physical locations in just a few clicks. Putting applications in closer proximity to end users reduces latency and improves their experience. No matter your location, size, or industry, the cloud frees you from managing infrastructure and data centers, so you can focus on what matters most to your business.
All right. So I'm going to chime in a little bit. I know that
please.
these are like
Hi
super
there. Welcome to
advanced
this brand
concepts.
new
Okay, I know these are super advanced concepts, and cloud and chips that what Rebecca talked about, like almost like air now these days, in the sense that we use it on a daily basis, but you guys don't realize it's even there. And that's amazing part. So I'm going to ask a couple questions to see what you guys say. And Rebecca actually kind of mentioned it. So we're going to see like how you guys listened. What are some of the things that you use on a daily basis almost that runs on cloud? You guys want to take a guess of combination of things? Okay. Computer, yes, but what kind of applications do you use on a daily basis almost that runs on cloud? Amazon, that's good.
Games, websites,
Google.
yes.
Zoom, that's a good one.
Mhm.
Okay, video games, that's right. YouTube, absolutely. Yeah. Definitely, like your favorite games you're gonna planning to do this summer, like Roblox, Fortnite, they all run on cloud. Okay. Where can you find chips? Like earlier on, Rebecca mentioned about chips in PS5, yes. No, what kind of hardware? So chips are, you think about hardwares that have chips in there. Nintendo, awesome. iPad, awesome. Wi-Fi routers, yeah, someone asked a question.
CPUs, GPUs, yeah.
Television, I love that. Think more, there are more places. Don't repeat, people have said. Alexa, that's a good one. Something else, think about something else. Siri, that's good. Yeah.
Streetlights is an interesting one. I'm not sure. That would be some advanced streetlights. It's not that it's impossible, but if you've had any kind of an automated sensor, so like you go by and use a hand dryer that automatically turns on when you're there, there's computing circuits there. Google Home, absolutely. Autonomous driving, so the automatic cars, absolutely. Yes, your Ring system is absolutely a computer. Even sometimes even cables sometimes have computers in them to manage power.
Yeah, definitely. Isn't that amazing? Like you don't realize the chips that like Rebecca showed you earlier on, it really runs everywhere. It's all over around us. You probably have thousands of chips in your house and you don't even realize they're there. Very cool. All right, so let me ask you another more advanced question. If you ever get a chance, like she showed a video about going into the fab. If you ever get a chance to go check it out, one of those, you should definitely go. Very few people can get a chance to go in there. All right, another question just to tell you like how amazing these technologies are. Let's see, for your let's say computer, how many transistors do you think like there are in a typical computer chip? Like there are actually many chips there, so I'm like being really loose with my questions. So Rebecca, you can correct me, maybe ask a more accurate question there. How many? Okay. When you have too many zeros, it's gonna be hard for us to count. Okay. 50 million. We have 1 million, 50 million. Okay, they're a pretty large range. All right, cool. Well, that's good guesses.
Not
I don't know
quite
how
infinite.
many actually.
It's about, I mean, one of the last ones that we produced from a client perspective, I think was about 60 billion. So it's, and that's a CPU. It depends on the complexity, right? So if you've ever, one of my favorite things to do with my 6-year-old is when his, you know, overall robots or whatever toy breaks, we totally take them apart and we'll go through and see the circuit boards, and you can see what's in there. And you know, many of those are far fewer than 60 billion transistors. But
yeah, 60 billion
cool.
transistors. How many? What's the population of the Earth? Like, you guys know what's the population of the Earth, roughly?
Yeah.
Okay. So if you have every person in the whole world hold 10 transistors, then they actually fit into a single computer on your computer. Yeah, so okay, I hope I didn't get the math wrong, but
No,
you get the idea.
Yeah, and that chip is about this big.
Yeah.
Right.
Just think about what kind of like super cool technologies are in there that enable things that we do on a day-to-day basis. Okay. All right. Sorry for interruptions. I just want to make sure that they kind of visualize a little bit what it's like. Go ahead. Keep going.
It's like you're a teacher, Jesse. I love it. Okay. So what do I do? So, you know, I've talked a little bit about how we fabricate chips and how amazing they are. I've talked a little bit about how we actually turn that into the internet and how that connects to end user experiences to create cloud computing. We've talked a little bit about how those transistors show up in your lives, in your phones, in your tablets, in your computers, and enable certain experiences like Roblox and Minecraft and Zoom and all of your wonderful ideas. Somebody has to put that together. So we have to go from the transistors and the CPU and the storage and the memory and all the different components that are created into systems. And those systems then have to be stood up with all these different companies that actually create those experiences. So in the chat, somebody mentioned Netflix. Netflix uses servers. Servers are there to help create an end user experience so that when you pull up your favorite, you know, show, whatever it may be, that can come to you on your tablet. That whole back end is running on servers in cloud computing model. So I work with those customers to make sure that they get their servers, that they have all the components they need for it. And I work with customers in the United States. I work with customers in China. I work to make sure that our products meet their needs. And I work to try and make sure that the key workloads that are growing and changing the landscape of computation are actually well understood. So areas like AI, for example, to try and make sure we're building the right things. Okay, let me go to the next. Okay, so let's talk a little bit about how cloud computing sort of happens. Try and connect those chips to those servers to end experiences that you have. Okay, we're going to start with the overall left side, right? So when I'm building a server and it runs, you can build one in your house, anywhere you want, but on somebody's location, it's going to have obviously a CPU. It's going to have some connection to the internet. It's going to have some local storage so that it remembers every day what you do. And it's going to have virtualization capabilities, potentially, depends on what you're running. But in the cloud, it certainly has virtualization. What is virtualization? It just means that your experience is in some ways isolated from other people's experience that may be happening on the same physical hardware. And then it's got all these different layers of software up to your end application. In this case, let's just take the example of Netflix for good reason. If I am going to have that experience in one server on my home experience, it's all happening and I'm managing it. That's what happens when I run a server at home. If I use cloud computing infrastructure as a service, then what's actually happening is that everything up to that virtualization layer is actually managed by somebody else. So rather than me having my servers, keeping them in an air-conditioned data center, making sure that the power is working and the cooling is working and all these other things, somebody else takes care of that part. And I just I log into the experience and then run from the operating system up to my end application. That's where I focus. So I focus on my application, not on the hardware underneath it. I use the cloud service, an infrastructure as a service provider, to make that happen. Now, there's even different models in this area. There's something called platform as a service. That's where you don't even see an operating system. You literally are just using an interface for data and application. Could be a database service, could be, there's many. Somebody mentioned Alexa. Alexa's not quite a platform as a service, but it's an area where you're speaking into something. It is taking that data and using a natural language processing model to understand what you've said, and then go access a platform as a service to get you an answer to your question, to play your favorite song, whatever it is that you're using. So that is a combination of a service, Alexa, and then a back-end database that actually knows the answer to your question, which usually does through lots of work in the internet. Oh, that's such a great question. Somebody asked me how Alexa does voice detection. It is something called natural language processing. Again, probably a whole nother hour of fun discussions on how we figure out what people are saying and turn that into a search and actually figure out how to render back to you the answer. So much fun to talk about. We should have a different time that we talk about it. The last area is software as a service. Think of this as, somebody put in the chat session, Teams. That's a software as a service experience, Microsoft Teams, to log in and do stuff like this. Zoom, this is a software service that we're using to do video chatting. So these are applications that you consume without knowing any of this backend. But Zoom has to do this backend. They have to make sure the application is getting data, it's managing its runtime, it's middleware, it's got an operating system, it's running on clouds, through virtualization on servers. So all of that work has to happen no matter how you experience it. So whichever service we're using, they may use any combination of these models to give you an end user experience. They may be fully hosted in the cloud. They may be completely hosted in their own data centers. Either way, this is the kind of stack that has to exist to help end users consume actual applications. We have good hand raising. Jesse, let me know if I should jump in or answer any more questions. Let's go to the next slide, Rach.
Okay, we're going to try to answer questions from people who raise a hand later on, but let's go through the slides first.
Okay, so maybe the whole internet seems complicated to think about, so I wanted to anchor in an example. So if I were to call myself a pizza as a service, for whatever reason, I wanted to kind of break down for you what it takes to make a pizza. So obviously you need a kitchen, to make sure that you have the right components. You need power to mix the dough, to make sure you're doing all the right things. You're going to need to make sure there's power coming into your kitchen. You need those tools. Obviously, whether it's a food processor or using your hands or a rolling pin, you have to have tools to make that happen. You need to have the components, the ingredients for dough, flour, salt, a little sugar maybe, water, to make sure that you're creating the dough correctly. Then you need the ingredients to make your favorite friend's best pizza, whether that's plain cheese or pepperoni or whatever it is that you like, all those toppings. And then you need an oven to bake the pizza, right? So these are, in some sense, the recipe, the tools, the combination from how you have to start in the kitchen. When you think about that from a computing perspective, if we kind of go back to the sand to silicon, the kitchen, that's our fabrication facility. That's how you build a chip. It needs power, it needs ingredients and many tools to build those chips, whether it's a CPU, a GPU, an SSD, a storage device. Then when you build a server, you have to put that together, right? You need to put a CPU, you need to put memory, you need to have a connection to the internet. It needs to be, somebody had mentioned a motherboard, it needs to be on a motherboard. You need to make sure that that runs. You need to connect it to power. You need to put it in a rack, put it in a data center somewhere, and make sure that it can serve end users' applications. So that's kind of the analogy of going from a chip all the way to a data center, whether it's someone's own data center or operating in the cloud. It's kind of just like building a pizza. Let's go to the next one. So if I took those same analogies and did it with pizza, running in your own data centers is kind of like making your own pizza at home. You did all those steps all at home, not the fabrication, but at least the consumption, the putting it together. The infrastructure as a service model is more like if I went and used a professional kitchen, so they have the kitchen, the gas, the oven. I come in with the pizza dough and the toppings. If it's platform as a service, it's a little bit more, they give me the pizza and I take home and cook the pizza in my oven. And then the last kind of software as a service, this is, Papa John's or whatever, delivering you a pizza and you get to eat the pizza. So just kind of wanted to anchor into something you've probably experienced before, at least if you're anything like my children. They love pizza. So this is kind of the different ways in which you could consume pizza. Cloud computing is just the consumption of data through applications, and it can be done in many different ways, just like making pizza can be done in many different ways. Okay. So I wanted to kind of end this part of the chat and then get into questions with what I love most about being in the space of technology, working on computation, working on computers. Don't be encumbered by history. Just go out and do something wonderful. This is a Robert Noyce quote. Our job every day is to build something interesting that helps unlock cool experiences for people like you in the world. And it's complicated. It continues to get more complicated in some ways, but that's not something to be encumbered by. We keep getting better in terms of our tools and our capabilities, and learning coding now using something like Scratch is completely different than how it was when I started learning coding. So I think we will continue to find new and interesting ways to make this world exciting together.
Yeah, very well said. That's super inspiring. So thanks so much, Rebecca. We have a little other segment, which is Javi is going to show us we're going to try to do something in the cloud together. This is an activity called pixel art. Javi, are you here?
How's it going? My name is Javi.
Hi, yes. So Javi is actually works on cloud as well, and he is an engineer at Airbnb, and he actually graduated from MIT as well. So you guys are actually alums, Rebecca.
Awesome.
Awesome. So Javi, can you maybe spend 5 minutes like walking them through the exercise? Another thing I'm going to do is I'm going to send a link to the chat right now. This is how we register for your attendance. If you are here for all the students, you know what your email that your parents asked to sign you in. You can put your email there so we know who are here. I also want you to think about what question you have for Rebecca. I'm sure you have tons of questions. This is one topic would take many years to learn well. Just ask what questions you have, and we'll do after Kavi done the demo, and then we'll do the exercise, and we're going to have Rebecca answer some questions. Go ahead, Javi.
Yeah, so should I share my screen?
Yes.
All right. So here's a little demo of a drawing app we made with using the cloud. The cool thing about this, though, is that if I share out this link, we can all draw together. These types of applications were extremely hard to make even 5 years ago, but because of the advances that we talked about earlier today, it's become so much easier. So I'm about to send a link out in the chat. So if everyone can click on it and start drawing on the app, like I can already see other people drawing things in a fairly real-time way. And this is kind of a cool, so people always talk about like the internet bringing people together. This is a literal way where we're all working together on the same thing. Yeah.
Can you guys see if you can collectively draw a smiley face emoji? Okay, people are picking different. Okay, I can see some people are doing it. Oh, did you send the link? Okay, yeah, so Javi has sent the link to the thing. One person said I cannot get on it.
Oh, really? Oh, no.
Some people can.
Yeah, I'm seeing their little dots pop up. And
I can feel like some people want to draw eyes. I mean, there's definitely that face yellow line there. Yeah, like if you're doing this collectively together, you can actually pick a part of the picture and try to do it. The way you do it is you can click on these of the colors and then try to color it.
Yeah, and there's also ways to pick your own color. If you click this one, you can go crazy.
Maybe someone can work on the mouse. Someone can work on the, the face itself.
Oh, there's no yellow on yours? Yeah, sometimes it takes a while for the information to go across.
Yeah. Okay, we're going to leave this on for a bit. Do you want to tell them a little bit about how this app is built, Javi?
Yeah, so we use a couple of technologies that we can actually look right here. You can view source and we can actually look at the actual code that does it. So we use this technology called Firebase that we learn all about in the cloud computing class. And right below here is all the code that does it. We can listen to when people click on it. And every time something clicks on it, we talk to this cloud service or this this service where that will store all the changes we make. And then if we really try, we can also upload our picture a little bit later. There's a little save button down here. I'm not sure if I pointed that out earlier. Oh, seeing a little bit yellow pop up. I can click save, and eventually I can save this version of the image for posterity and all sorts of things. So all this code was written pretty concisely. If this code is much shorter than it would have been in the past. It's because our tools have become so much more powerful.
Cool. Very cool.
Yeah.
So we're going to leave it. So you guys should let's try to see whether we can collaboratively build a little smiley face here. Don't change other people's color, try to build on it. And maybe we'll come back and after Rebecca's Q&A session to see, what you guys have created. Okay, so can you unshare, Javi, if you don't mind?
No problem.
All right, so if you guys have questions, I'm going to start. Let's see. I'm going to start calling your name and then you can ask questions, okay? And then if you're not asking question, please lower your hand. Okay, I'm going to ask. Would unmute. Okay. The gamekeeper. Someone's name is like your Zoom name, and is the gamekeeper. Do you have a question?
Yes. What script do you guys use? Do you use JavaScript?
Is that a question on the application we were just looking at, or do you want? There's lots of different scripts used on the internet, so we could talk about it for a while. But maybe if you just want to ask your question in what is your question with respect to JavaScript?
So so in the Java, like most scripts, like usually I do Scratch, which is the easier one. And there's another one which is Python. It's kind of like Scratch, but except that you have to write the code down. And
Yeah.
And how come you have to write the code?
Well, different tools, different things. There's a lot of power in writing the code and telling the computer specifically what you want to accomplish versus trying to kind of, when you're doing it to make a game, you have a visual thing you want to do. And so sometimes you can be more efficient for the end user's time, right? You as the builder of the game to use that interface versus writing it by yourself. But if you were writing an application to go search a massive database, trying to do that through some sort of a visual, like imagine a table that has, you know, hundreds of thousands of lines. Like, could you imagine scrolling through that to find the one you wanted to do versus just writing a quick little line of code that said, hey, find me something that says Alistair. And that's a lot easier to move forward and do. So some things are more efficient to do them visually, some things are more efficient to write.
Cool. Yeah, that's a good question. I mean, coding by itself is a huge area, and obviously everything that Rebecca talked about in cloud takes a lot of code to write. You know, sometimes it's Python, sometimes it's JavaScript, and sometimes it's something else. Okay, let me see, ask another question. Alice there?
Yeah.
Go ahead.
No one else is drawing smiley faces except for me.
You're trying pretty hard. Thanks for being collaborative. I know it's kind of hard to collaborate on the same piece of software.
You're just doing dots all over. Can you see that I drew like 3 smiley faces?
Okay. Well, we see everyone else should listen to Alexia and try to draw the smiley face. Okay. All right. So let's see if I have questions. And Zara, do you have a question?
Yeah, so for Intel, like what software do you use? Like, would you use JavaScript or Java or Python? Because if you use Python, I think it would be a bit hard because you write down the code usually in Python.
Oh, we use so many different kinds of scripts because source, what you're building is different. So when you are building a chip, you use something called a register transfer language. It looks a little bit like C code, if you're familiar with C, but it's describing hardware behavior, and hardware happens in parallel. Everything's happening all the time. You know, when I'm doing something on my phone, lots and lots of different parts of the chip are simultaneously moving. So you describe it a little bit differently than if I'm writing something like Python on a computer, which has an assumed, what we call a von Neumann architecture, right? Where it goes one line, then the next line, then the next line, then the next line. So hardware is sort of like lots of things happening in parallel. Software assumes it's going to happen in a linear fashion. There can be different applications that are happening at the same time. So it's not that different, but the way you code a single piece of software is sort of assumed it goes down.
Yeah, and when you're, and like when you sometimes use your computer for certain things, you also use different. So if you like say if you use Intel and you write a Python and like if you write one code wrong, would the whole like system be wrong? Like will everything go wrong?
Well, usually if you're writing code, you submit that code to a compiler or an interpreter, and in that phase of compiling or interpreting the code, it'll tell you if there's a problem. You've probably seen this in your coding classes. So that little step is what makes sure we create what we call usually a binary, or it depends on the different kind of code you're writing, but creates that final application and make sure that there's nothing wrong with that application. So you want to go through the testing part of it and making sure it's correct before you actually tell the computer, go do this. So there's kind of a phase in between before. So yes, if you gave the computer really, really bad code, sometimes bad things can happen. But in general, if you write your code, you're going to go through a phase first to make sure it correctly compiles or correctly runs within the browser or whatever, however you're running it.
Very cool. Do you have 5 more minutes, Rebecca? I know we're running over.
I think I do, yeah.
Okay, thank you. So I'm going to ask 3 more questions. I'm also going to ask everyone to think about what you have learned today. Don't type it in the chat yet. I'm going to ask you what you have learned today. Tell us one thing that you learned today and later on. But for now, I'm going to ask Brista, can you ask your question?
Why is it that when they're showing how they're making the silicon chips for Intel, none of them were actually covering their nose, even though they want the air to be 100% pure?
Oh, I love that question. It's such a great question. I honestly don't know why they had them here versus there. I think we've all learned over the last year to keep your whole mouth covered. I think it was mostly your mouth and your nose. I think it was mostly so that they could take the videotape. So depending on which fab you're in, some people have like the full kit, everything is covered. Some have masks that go over your nose and your mouth. Different facilities have different requirements in terms of the purity of the air. And so there's slightly different protocol depending on which. But yes, you should have everything covered. It's a good catch.
Awesome. Next one, I have Achueta. I'm not so sure I'm saying your name right. Achuta.
It's Achuta. Okay. And I just want to ask, how big is are there transistors currently?
Are the
transistors?
How big?
So I think you saw on there that we were looking at transistors that were smaller than your hair, thinner, tinier than your hair. They're so tiny, it's hard to even visually picture it.
Yeah. It's amazing, like how they can build something like that and then create chips. It's just like truly amazing. Last question, and again, I want everyone to think about say one thing of what you have learned later on, but don't type it yet. Isa, can you say you? I think I tried to unmute you. Go ahead.
Okay, so how big are chips usually, or mini chips?
Yeah, so we talked a little bit about like a computer processor chip, which is smaller than the palm of your hand. Obviously, the ones that are in your cell phone are even smaller. They are also CPUs, but they're even smaller. It kind of depends on what you're building. So there's everything from tiny little microcontrollers that can be like, that big, to massive server class CPUs, to, if you've ever seen a GPU, like the NVIDIA GPUs, those are pretty honking big for, again, a processor of a variety, right? It's a graphics processing unit, so they're about this big. They don't tend to get a lot bigger than that. What's interesting is that we're in a world of silicon at this point where we're stacking things in 3 dimensions in order to be able to get more density in smaller spaces. So we've done a lot to sort of increase the number of processors we can print, and now we're going 3D as well through FinFETs and now stacking technologies in the manufacturing of chips. So there's so many cool standards. If this is something that's interesting to you, because I totally could nerd out about this all day, Hot Chips is like one of the industry sessions, and they have lots and lots of videos online about some of the cool stacking technologies and how it works, to be able to actually, have one current of electricity running consistently through all these different packages. And then there's all sorts of cool ways in which you have to verify that it's doing the right thing so that we can actually have our experiences work correctly.